Hello, welcome back. Today we're going to talk about series and parallel electric circuits. Specifically, we're going to talk about the difference between a series circuit and a parallel circuit. And we're going to actually do it at two different levels. Here in the beginning, we'll talk conceptually, without any math at all, how a series circuit behaves and a parallel circuit behaves. And we'll talk about why we even have different types of circuits in the first place. And then we'll transition to going a slight level deeper, just for those who really want to get more of a deep understanding with a couple of simple examples at the end. So you can certainly watch half of it if you want and understand the concept completely, or go all the way to the end for a deeper understanding. So why do we have two different broad classes of circuits anyway, series and parallel? Well, really, it just depends on the type of circuit you have and the application you're going for. It's simpler to wire things in series, and so it might totally satisfy what you're trying to do to wire things in series. But for certain applications, which we'll talk about in just a second, wiring things in parallel makes much more sense and it's more robust, but it's a little more complicated. So we're going to talk about the difference here. So let's first draw a very simple situation for a series electric circuit. And we're going to talk about light bulbs and voltage sources. So I'll refresh your memory as we go along here, but let's just start with a battery of some kind, or some kind of voltage source with a positive and negative terminal, and we're going to say this is 10 volts. I'm going to remind you what 10 volts actually means in just a second here. Now, wired up to this thing is a wire which goes in this direction, and then over here on this side of the circuit we have a light bulb. And the symbol for a light bulb, there's a couple of different symbols. You might see a squiggly, curly wire inside to represent the filament, or just a big X inside. This is a light bulb. And we say that in series with that is a second light bulb, just like this, another big X like that. And it's connected to the other side of the battery because, as you know, for a circuit to function, you need to have a closed loop for the electrons to go around like this. All right, now before we get and talk about series and parallel, I want to remind you that when I say 10 volts, the voltage in a circuit does not flow anywhere. The voltage in a circuit is like the pressure in a water hose. It is the push that pushes the electrons around the circuit. So if you have 10 volts, it represents a certain amount of push. If you have 100 volts, it represents 10 times more pushing, for lack of a better word. It's really called potential. So you might think about or hear voltage sources talking about potential or potential difference. Another way to think about it is if you think about a mountain. If I draw a mountain here, then halfway up the mountain might be representative of 10 volts of potential. Because if I'm standing halfway up the mountain, I can certainly throw a rock off the edge and it will go screaming down the mountain and pick up kinetic energy. It had potential energy halfway up the mountain. When you throw it off, it goes down, rolling down, and converts into kinetic energy and can do some damage down there. But if instead I go 10 times higher to the peak of the mountain, maybe that represents 100 volts at the top of the mountain, then certainly any rock I throw at the top is going to have a lot more potential when it rolls all the way down to do more damage. So I want you to think about this number just being a number indicating how strong or how much potential these electrons have in terms of their pushing force, for lack of a better word, coming around and allowing those electrons to circulate around the circuit. So for now, we're just going to take 10 volts, but it could be 5 volts, it could be 3 volts, it could be 10 volts, and that number just represents how much of a pushing you have coming out of that source there on the electrons. And this is also a DC source, direct current. And a DC source is just a source of constant, it produces a direct current or a constant current. So the voltage never changes is what that basically means. All right, so what you have here is you have the situation where you're going to have an electric current circulating here. So you're going to have a current, which we're going to say goes here, and I'm going to call it I sub S, or actually I'll just call it I. The current I. And this current also goes down through the light bulbs here. Now, crucially, for a series circuit, because everything is connected in a single line like this, the current that comes out of the battery or the voltage source is the same amount of current that goes and flows through the light bulbs. So what is electric current? Current is the thing that's actually moving. Just like in a stream, right? The stream has water flowing through it. And we would say that a faster moving stream or a wider stream with more volume of current has more current. Same thing in a circuit. It's more electrons flowing per second around the circuit. That's what's actually doing the work of the devices in there, whether it's a motor or whatever else the circuit is actually doing. And just like a stream could be on the side of a mountain, a stream with one end at 10 volts up halfway up the mountain would allow the stream to move down into the bottom of the mountain. Then it has to go back to the source to go back up and create a circuit again. So you can kind of think of these electrons or this current coming out to the side, and then when we re-enter the source, they kind of get accelerated again back up to the top of the mountain to go all the way down again and again and again, flowing down the mountain. Okay? Now, one last thing I'll say. This current here, in real electric circuits, the electric current is electrons that flow. Electrons are in the outer shell of all of the atoms, and in metals, electrons are what actually can hop from atom to atom and actually flow. Now, we have a negative terminal here, so in reality, the electrons are flowing out of the negative terminal and going this way. So why did I draw the arrow this way here? Well, it's because electrons are negative. And the convention over the years has developed that instead of writing the negative electron flow one way around the circuit, we just pretend that it's oppositely charged, positive charges flowing around the other side. So we know that we really don't have actual positive charges flowing this way, but it's the same thing mathematically as having negative charges flowing this way. So if you don't like that, fine, erase the eyes and draw an arrow this way and say it's electron flow, fine. But in reality, we always draw electric current in circuits as coming out of the positive terminal, even though actually it's the opposite electrons flowing the other way. Mathematically, it's the same thing. Now here's the deal. In a series circuit, both of these bulbs are illuminated when the current goes through there, okay? If I remove this bulb, or if I just smash it, or if this bulb burns out, what's going to happen? Well, the electric current is going to not be able to pass through this one. And so because it can't get through it anymore, if you physically remove it, then it cannot continue the journey. And because this bulb is in series, this bulb stops working. So the main downfall or the main issue with series circuits is if one of the devices burns out or you remove it, the other device, the other bulb, stops working. And that's kind of not great. If you have 100 lights in your front yard and you wire them in series, one of those lights burn out, then the entire string of lights stops working. Because when one of them gets burned out or removed or smashed, the electric current cannot continue to flow around, and that is just the way it is. Now, it's very easy and simple to connect this, but that is the main downside there. All right, last thing I'm going to say is the same current, the amount of electrons per second, flows through both bulbs. So both of these bulbs, because they're in series, they have to be illuminated with the same intensity of light. If you hook two bulbs in series, by definition, if the bulbs are the same, then they have to be illuminated to the same intensity because it's the same current, the same number of electrons per second flowing through both of them because they are in series. All right, now what we want to do is we want to compare and contrast that with a situation where we have a parallel arrangement. So down here, I'll put parallel. All right, parallel like this. Now, for completeness, I'll have the same voltage source. So plus minus right here, 10 volts. Remember, this just represents how much pushing force I have. And of course, it's a DC, which means it doesn't change over time. And then what I'm going to do is have the same bulbs right here. Here's one of them. And I'm going to have an X right there. So that's one bulb. But instead of putting the other bulb directly in a line with it, that would be series, what I'll do is I'll branch off from here and connect a wire over here and have it go through its own bulb in its own branch. So I'm introducing a new word for you. It's called the branches of the circuit. This is the first branch and this is the second branch. When you think of branches of a tree, you think of the branches splintering off and kind of going different directions. And so that's what's really happening here as well. In this situation, there is electric current going out through here, right? But when the electric current gets to this point, it hits a branching situation where some of the current has to go down through this bulb and some of the current has to go across through the other branch. So what I'll do is I'll call this being the source current here, and I'll label this I1 and I'll label this I2. And what's going to happen is when the electrons are all in a single file line, when they get to this point, some of the electrons go around this way and some of the electrons go around this way. And when they rejoin to the other side, they once again go back in a single file line back to the source. So without doing any real math, you can see from this that the source current I sub S is got to be equal to the branch current I1 plus the branch current I2. So however many amps, that's the unit of current. It relates to how many charges per second, coulombs per second, are flowing past a point, electrons per second. However many amps it is, it has to be equal to whatever this is plus this is. Because for every electron that goes in here, it has to go either down or over. And so when you add them all up, they have to come back together again to flow back through the source. All right? Now, the crucial thing about parallel circuits is that if I smash this bulb right here or take it out of the circuit, what's going to happen? Well, there can be no current flowing through here anymore because it's now an open connection and it can't go through and continue its journey. But this branch is unaffected by that. And so the current can continue to flow through this branch of the circuit. So whereas before, if I smash this bulb, both bulbs stop being illuminated. Over here in parallel, if I smash this bulb continues to be illuminated. Now, you can see that this has lots of advantages, right? In your house, you have light bulbs all over the house on the same circuit. A lot of times in the same room, you have outlets on the same circuit. If I smash a light bulb or if it burns out, it doesn't affect the other light bulbs in the house. That would be terrible for one to burn out and everything to go out. Same thing with your lights in the front yard. You don't want that. So for lights, it doesn't make sense in general to put them in series. We absolutely have uses for series circuits, but for light bulbs and long strings of light, they're never wired in series because of this. But that is the main difference I want you to pull away from a concept point of view. In series, the same current has to flow through both. So if I smashed one, then both of them stop illuminating. But over here, you have different currents flowing because the current branches off. And so if I smash one or break it, then the other bulb continues to be illuminated. One other crucial thing to know about parallel circuits is that notice that this is 10 volts, and you can think of voltage as being how high up the mountain you are. How much potential are you giving? How much pushing are you giving these charges flowing around the circuit, right? Electrons coming out of this end, fictitious positive charges coming around this end, all right? But since this battery is connected through a perfect wire to here, and since it's 10 volts from here to here, then we know that there must exist a 10 volt voltage drop across this light bulb. And because this light bulb is also connected directly to here, which is also connected directly to here, and remember, we're assuming perfect wires with no loss in any of the wires, like perfection. We don't have actual wires that behave like this, but these wires don't have any influence or losses at all. Then we say, because this is connected directly to the source, that this also has a voltage drop of 10 volts, right? So that's another way of looking at it. Because the source is physically connected to across both, you have a 10 volts of potential to push current through each of these branches. And because of that, if I smash this one, I still have the 10 volts that is connected across as a pushing force through this bulb. And that's why this bulb can remain illuminated, because it has its own voltage drop across it because it's connected like this. Whereas in series, notice that they're not directly connected across the battery, and so they're dependent on the same singular path going all the way around. So that concludes the conceptual part. You should have an overview of the difference between series and parallel circuits. If you want to stop here, that's fine. However, I encourage you to continue with me to the end, because it's not hard and you'll get a deeper understanding of what's going on. Now, to continue, I want to talk about light bulbs a little bit. Light bulbs glow because they have what's called resistance. Resistance is when the current that's flowing in the circuit, the electric charges, are impeded or have a resistance. Wires, like copper wires or gold or silver, most metals, conduct electricity very well, very easily. And it's because there's so many electrons in the outer layer of the atom, the outer shell of the atom. And so it's very easy to move electrons around. But in things like rubber or plastic or wood or even water, unless you dissolve salt in water. Water is not a good conductor of electricity either, because there's just not very many mobile electrons outside to be moved around, okay? So inside of a light bulb, there is a filament, and that filament is constructed of something that has some it allows current to flow, but also it gives a little bit of resistance. And that resistance causes friction. When the electrons go through, everything gets agitated and they start to glow because of the friction. And the light that we see is literally because of the friction from the electrons going through there. So I guess what I'm trying to say is these light bulbs here, I've drawn them as light bulbs in this circuit, but you can consider them being a new circuit component we haven't talked about yet called a resistor. A resistor is just impedes or resists the flow of current. The higher the resistance, then the more it tries to shut down the current flow. All right, so let's talk about that. Let's go over here and let's basically redraw this circuit, and instead of light bulbs here, we'll just put resistors in place because that's effectively what they are. What we have here is we'll do the same 10-volt source, it's still DC, but instead of a light bulb, I'll draw this little squiggly line, which will be a resistor, and in series with it, I'll draw another squiggly line right here. So they're in series, exactly the way that they were just a minute ago. Now we have a new unit here. How much resistance does this thing have? We'll call it 5 ohms. This symbol means ohms, 5 ohms. All right, so the way circuits works is like this. You have a push called a voltage. That's how much push the battery is trying to shove the electrons to go around the circuit. But the electrons are encountering resistance. And the higher the number for the resistance, the more they try to shut down the current flow. Now, as a result of the push and how much resistance is there, some sort of current is allowed to flow. And the more resistance you have, then the less current that is allowed to flow. All of this stuff is summarized through a really important equation called Ohm's law. Same ohm as this unit here, Ohm's law. And Ohm's law is that the voltage across any circuit element is equal to the current flowing through any circuit element multiplied times its resistance, if it's a resistor. This gets more complicated for alternating current later on, but this is the basic idea. So if you use algebra to solve for I, here just divide both sides by R, you'll get I is equal to V over R. Right? So what this means is that the current flowing through the circuit gets larger if I give more push with V on the top. But if I increase the resistance because it's on the bottom and I'm dividing, then the current goes down. So more resistance shuts down the current flow, just like I told you. More push from the voltage means more electric current. So the current is a result of how much voltage you're pushing with and also related to how much resistance you have in an inverse way. Now, you have these two light bulbs and these things are in series. In series, when you have resistances in series, you can think of an equivalent resistance. Equivalent, when these are in series, every electron that goes through this resistor must next immediately flow through this one. And if this one is representing 5 ohms of resistance, and this one is also representing 5 ohms of resistance, in series, the equivalent resistance, this is a series circuit, the equivalent resistance, you just add the resistors together. So 5 plus 5, so the equivalent resistance is 10 ohms in this case. All right, 10 ohms in series. It's a different equation in parallel, but in series, any resistance you have, you just add them together. If you had another resistor here, like another 10 ohms, then you would just add it together to these. If you had 100 ohms and you had 100 resistors all in one after another, daisy chained, you would just add them all together, and that would be the equivalent resistance that the source kind of sees when it looks this way. So to figure out what the current that's actually flowing this way is, what you do is you use Ohm's law. I is equal to V over R. But you use the equivalent resistance because from the source point of view, it's connected to what looks like 10 ohms because they're in series here. So what you do is you say that the voltage here is 10, and the resistance here, I'll put volts here, and the resistance is 10. So you have volts and ohms, which is the correct units. And so what you have here is 10 divided by 10 is 1, and the unit of electric current is amperes. And the ampere is a unit that relates to how many charges per second are flowing past a point. It's directly related to how many charges per second are flowing. All right, so we're saying that there's 1 amp of current in this situation. Now let me ask you a question based on your conceptual understanding. If we inserted another resistor, like put 3 of them in a row, instead of 5 and 5, we had 5, 5 and another one, would the current go up or down? Well, you're introducing more resistance in the same path. So the current has to go down in series when you add more resistance. So let's do that, because this current here, this 1 amp current is flowing through this resistor, and this 1 amp current is also flowing through here. It's the same current flowing through both. And the reason it's the same is because they're both in series, and every electron that flows through the first resistor has to flow through the second one. So it's the same number of charges per second flowing. That's why the current is the same there. Now let's go down and amend this circuit as we talked about here. So let's say we have a 10-volt source, and we'll have 1 resistor, and then I'll put another resistor, and then as promised, I'll put a 3rd resistor here, like this. And then what I'll say is, we'll keep the original 2 resistors, 5 ohms, 5 ohms. These are the original 2, but all we're going to do is add another one, and just to make it a nice round number, I'm going to make this one 10 ohms. So what would happen in this situation? Well, the equivalent resistance, remember for series circuits, you can just add the resistors together. They are in series, so we can add them. We have 5 and 5 is 10, and 10 more is 20. So the equivalent resistance is 20 ohms, right? And then after you have the equivalent resistance, to figure out what the current is, the electric current must be the same flowing around. It's the same exact current flowing through all 3 of these. The current I must be equal to V over R, which equals to the voltage, which is the voltage across the equivalent resistance that you see looking this way, 10 volts. And even though it's 3 resistors, it looks like a single 20 ohm resistor to the source, right? And so since 10 divided by 20 is 1/2, then you can just put that as a decimal, 0.5 amps. Now notice what happened here is that in the original case, we had only these 2 5 ohm resistors, and the source was pushing 1 amp of current that's related to how many charges per second that are coming out of the source feeding the rest of the circuit. As soon as we added another resistance here, it caused the current to be supplied by the source to go down, which is exactly what we said conceptually should happen. In series, if you increase the resistance, the current has to go down. That's what Ohm's law is about. And if these were light bulbs instead of resistors, right? If this were a light bulb and a light bulb, then this current would be causing them to be illuminated with a certain amount of illumination. As soon as we added another light bulb, let's say this light bulb had a higher internal resistance, the current would be lower, much, much lower, actually reduced by half through all 3 of them. It's the same current through all 3, and so that means all 3 bulbs would be dimmer than, or these 2 bulbs, I should say, would be dimmer as compared to the original because there's less current flowing through them. Now let's do the same exercise with parallel circuit. Just take a quick example to give you a little bit more comfort in knowing what you're talking about. Here is a voltage source. We're going to call it 10 volts, same as before. And here, instead of in series, we have a resistor in parallel, and then we have another resistor in parallel. That's what we have. Now, what resistances do we have? Just to keep it consistent, let's say this is a 5 ohm resistance, and this is a 5 ohm resistance. Now remember, how does it work in parallel? Well, in parallel, there is some sort of current coming out of here. We'll call it the source current, I sub S. But that current is not the same current that's flowing through these resistors, because when it hits this point, the electrons have to go, some of them this way and some of them this way, just like a river. When a river forks, some of the water goes this way and some of the water goes this way. So the sum of the two forks that fork off, it has to be the same amount of water coming from the source. So there's going to be some current going here, I'll call it I sub 1, and there'll be some current going through here, I'll call it I sub 2. And whatever these 2 currents are, they must add up to whatever the source current is, because it's just electrons per second flowing. They have to branch and then come back and go back through the source. But also we said that because they are in parallel, this is a 10 volt source and it is physically connected across here. So I know that there is a 10 volt drop across this resistor because it's connected to that voltage, right? So there is a push through, from top to bottom, almost like from top of a mountain to the bottom of 10 volts. And the same thing here. There is a 10 volt drop from top to bottom because it's physically connected directly to the source. In series, these things were not connected to the source. They were in line with one another. So because of this, we can then figure out what is going on. We can find what I sub 1 is. It's just going to be the voltage across divided by the resistance of the material. You see, Ohm's law applies to every single element in the circuit. The current flowing must be equal to how much voltage is across divided by the resistance. And so here, the voltage across is 10 volts, and the resistance is 5 ohms. And so I sub 1, 10 divided by 5 is 2, and the unit is amperes. So that's what the current flowing down there is. Now we can do the same thing over here. The voltage here we know is 10 volts because it's connected here. So I sub 2 is going to be 10 volts, and again, it is also 5 ohms, right? And so I sub 2 is going to be 2 amps. Now, because we know that there must be 2 amps flowing here and 2 amps flowing here, and these current branches have to be coming back through the source, then we know that the source current has got to be equal to whatever I1 is plus I2. And we know that that's 2 plus 2. And so we know that the source current has to be 4 amps. That has to be. And so what we figured out in this case is that the 4 amps that is supplied by the source splits equally. And so equal amounts of current, 2 and 2, flow through here. Now the only reason that it's equally splitting is because the resistances that I chose in this example are equal resistances. We're going to find out in a second that if I change one of these numbers, then it's going to just, in a proportional fashion, flow through in proportion to what those numbers are. And so if they're not exactly the same number of ohms, then you'll get a different amount of current flowing through each branch. So let's see that in the next one here. We're going to draw the same circuit. So let's redraw the same circuit, and then we'll add one more branch onto the right. So what we had is we had a single source. It was 10 volts. And then we had a single resistance right there, which I'll label in a second. And then we had another resistance right here, which I'll label in a second. And this was a 5 ohm here and a 5 ohm here. Now what I'll do is I'll just add another resistance over here, and we're just going to see how it changes what the circuit does. Now instead of 5, I'm going to make this 1 ohm. Now let me ask you what you think should happen. Yes, there is going to be some electric current flowing out of here. It's going to branch here, and branch here. Then it's going to recombine and go up through there. But you see, from the source point of view, if you're like an electron and you have a choice of going through a really high resistance, another really high resistance, or a really low resistance, what are you going to choose? Now, electrons don't have a choice. They don't have a brain. But basically, they try to follow the path of least resistance. So it's going to predominantly mostly flow through this branch. Some will flow through here and some will flow through here, but most of the current will flow through the lowest resistance. Let's see what happens. Now, we can label this as I sub 1, we can label this as I sub 2, we can label this as I sub 3. Now we've already calculated I sub 1 and 2, but we'll do it again real quick. I sub 1 is going to be V over R, and the voltage here is 10 volts because it's connected across. So just like before, it's 10 divided by 5. So that's going to be I sub 1 is equal to 2 amps. And I sub 2 is going to be V over R. We have 10, and we have 5 ohms. This is the same calculations from before, so 2 amps. So this is all the same. But what do we have over here? For I sub 3, it's going to be V over R. The voltage is still connected over here, so there's still a voltage drop of 10 volts across, but only 1 ohm of resistance. So 10 divided by 1 is 10 amps. So notice in words we said that most of the current should flow through this branch, and that is what happens. 10 amps flows here and only 2 here and 2 here. So the source current must be the 2 amps from here plus the 2 amps from here plus the 10 amps from here. So the source current, 14 amps. So the current should be 2 amps from this branch, 2 amps through this branch, 10 amps through this branch, and you add them all up, 14. So when they recombine, there's 14 amps is what's coming out, and it's branching like this. So that was the last thing I wanted to talk to you and make sure you understand about parallel circuits. If I remove this bulb, then these bulbs continue, if they're light bulbs, they continue to be illuminated. If I remove this one, then the current is still flowing here, so they're still illuminated. If I remove both of them, then the current is still flowing through there, so it's illuminated. So they all remain illuminated. And the voltage across each of the items in parallel are exactly the same. That's another important difference. And the last thing is that if you have items in parallel, the current will split in such a way so that most of the current flows through the lower resistance items, and relatively speaking, less current will flow through the other higher resistance elements. And that's it, an overview of series and parallel circuits. And I hope that you've enjoyed the conceptual discussion of it. What should it do? Everything we learn should have a conceptual understanding behind it. And then we get into the details where you can hopefully gain a little bit more appreciation. Please let me know what you think. Drop me a line, and I'll see you in the next one. Learn anything at mathandscience.com.